Good day and welcome back to part 3 of our discussion on volumes. In this video I want to just continue on our investigation and work through several more common examples that we can expect to encounter. For the first problem we are asked to sit up, but in this case we do not need to evaluate, an integral that represents the volume of the solid obtained by rotating the region bounded by the curves y equals x and y equals x squared about the y-axis. And just for good practice, let's go ahead and make the problem have two parts. In part A, we will rotate about the y-axis. In part B, we will rotate about the x-axis, so we can directly compare side by side the differences in the process. And this is an ideal scenario for you to get some practice in. So I would strongly encourage you to pause the video and give yourself 5-7 minutes and make sure that you can sketch the regions and then set up that corresponding integral. And for each case you should sketch the region and sketch a corresponding washer. And we've now reached the point where we probably won't sketch the solid itself all that often, but enough to see what's going on visually. So pause the video, give yourself a few minutes, see if you can set up these integrals. So in the first part, we're going to think about rotating about the y-axis, and in the second part, we're going to think about rotating about the x-axis. In either case, we're going to have the same region. So enclosed by y equals x and y equals x squared. And note, these two curves intersect at the point 1, 1. And we're forming a solid by taking this region and rotating it about the y-axis. So since we are rotating about this vertical line, using the method of washers, the volume is going to be determined by the definite integral over how the y values vary, and we're going to integrate a of y. The y values vary from 0 to 1, so we need to think if we pick a y value somewhere between 0 and 1, what would that corresponding washer look like? Well, we would take this small horizontal line segment and we would rotate this line segment about the y-axis. And that would create for us kind of this standard washer where we have a larger circle with a smaller circle removed from it. So the generic formula that we have depends upon finding the radius of the big circle, call it big R, and the radius of that little circle. And we should be able to clearly identify these quantities in our picture. So the radius of the small circle would be the distance from the curve closest to the y-axis to that y-axis. And similarly, big R would be the distance that further curve is away. So big R, and note we do want to get this in terms of a function of y, so this would be x equals the square root of y. So big R is simply going to be square root of y, and little r is going to be y. So the area of our washer, a of y, would be pi times the square root of y squared minus pi times y squared. And in this case, that would simplify very quickly to y minus y squared with the pi factored out. So the volume of this solid of revolution, formed when we rotate the region about the y-axis, is the definite integral from 0 to 1 of pi times y minus y squared. And this is what I would consider the sit-up portion of the problem. That is, you get it to the point where it's a definite integral and it's ready to evaluate. Let's now think about what would change if we were to rotate this region about the x-axis. So to begin, let's just sketch our region. So we have y equals x and y equals x squared. Note the point of intersection is 1, 1. So our x values are varying between 0 and 1. And we take the region and we rotate it around the x-axis to form a solid of revolution. And using the same observation as previously, we are going to integrate now a of x, the cross-section associated with an x value, and we integrate over the interval which the x values vary on. They vary from 0 to 1. And we need to think about a given value of x between 0 and 1, what that washer would look like. So we look at the vertical line segment sitting above x in our region, and we would have to revolve this about the x-axis. So once again, we get a very standard looking washer. We have a big circle with a smaller circle hollowed out of it. So we need to think, what is the big radius? What is the small radius? So that we can determine the area of this red shaded region. So in our picture, we once again should be able to identify this pretty quickly. So the small radius is the distance that closer curve is away from the x-axis. And the big radius is the distance that further curve is away from the x-axis. So big R is going to be x. So we're thinking in terms of functions of x because that's what we're integrating. And little r is going to be x squared. And with that in mind, the area of our washer is pi times big R squared minus pi times little r squared. And similarly, again, we can simplify this if we want. Pull out a pi, and we have an x squared minus x to the fourth left over. So the volume of this solid when we revolve the region about the x-axis is the definite integral from 0 to 1 of pi times x squared minus x to the fourth. So this completes the example, but I really do want to encourage you to make sure that you go through and understand kind of the subtle differences involved when we are revolving around a vertical versus a horizontal line. And we will look at one more example of finding a volume using this washer method. For our remaining example, let's find the volume of the solid of revolution obtained by rotating the region bounded by y equals square root x, y equals 0, and x equals 1 about the line x equals 2. So let's start by drawing the region. So y equals 0 corresponds to the x-axis. Then we have the line x equals 1 and the curve y equals the square root of x. And if we get rid of some of the extraneous portions here we don't necessarily need, we can note that once again this point of intersection, just by coincidence, is 1, 1. And we would like to take this bounded region and form a solid by rotating it about the line x equals 2. And note when we rotate this around the line x equals 2, we form a solid of revolution. And I'm not really going to attempt to sketch it, but instead note we're rotating about a vertical line. So we're going to be thinking in terms of functions of y, because we want to think about what our typical washer would look like. So if we pick a value of y between 0 and 1, we'll take this small horizontal line segment and we would rotate this line segment about x equals 2 to form our washer. Now I'm going to even go ahead and draw this in here. Hopefully it doesn't complicate the picture. And we get a very standard looking washer. But I just want to make sure that we all see kind of how that washer is being formed. So we have our generic washer, a larger circle with a smaller circle hollowed out. And in order to determine the area of this washer, we once again need to determine what is its big radius, big R, and what is the smaller radius, little r. And we can see these, I hope, very clearly once again in the picture. We have little r is the distance that closer curve is to the line we're rotating about, and big R is going to be the distance that further away curve is to the line we are rotating about. So what I would like you to do, and remember we're thinking in terms of functions of y, is to pause the video and take a moment and just write down a formula for little r and a formula for big R. So hopefully you've done this. So we have big R is going to be the distance this bigger curve y squared, x equals y squared, is from the line x equals 2. And remember, when we're trying to calculate this distance, we're always going bigger minus smaller. So x equals 2 minus x equals y squared gives us a positive number representing big R. Little r, similarly, would be 2 minus 1. So a of y is going to be pi times big R squared minus pi times little r squared. And simplifying this algebraically to make our integral as simple as possible, we pull out the pi. We have y to the fourth minus 4y squared plus 4 from the first part minus 1 coming from the second term. That combines together as y to the fourth minus 4y squared plus 3. So the volume of this solid of revolution is the integral over how the y values are varying, 0 to 1, and what we integrate is a of y. So that would be the definite integral from 0 to 1. Let's pull the pi out, and we have y to the fourth minus 4y squared plus 3. And getting it to this point is really the new part of the problem. This resulting definite integral is hopefully fairly reasonable and efficient for us to evaluate. So let's go ahead and do that. We have the pi hanging around out front. We anti-differentiate term by term, 1/5 y to the fifth minus 4/3 y cubed plus 3y. And we evaluate by the fundamental theorem of calculus from 0 to 1. Note when we substitute in 1, we get 1/5 minus 4/3 plus 3. Then we put a minus sign and we substitute in 0, which just gives us back 0. So we have our desired volume, and I'm going to leave it precisely in this form. So this finishes up our current discussion of finding volumes using the Washer method, and this is the last kind of example we will go over for now with the Washer method. In our next video on this topic, we'll explore 2 additional examples. The first of which is kind of working backwards. Maybe if we have an integral representing the volume of such a solid, can we explain the solid? That is, write down a corresponding statement like the question itself. And then the second example we will look at will explore and hopefully illustrate the limitations of the Washer method. When it works well, but there are scenarios where we run into some complications. So for more, stay tuned and take care.